So I look at this for a few different ratios of T1 and T2, which are what we might expect to find in quantum dots. A few different ratios of measurement errors over preparation errors. A few different time scales for the entangling gates. I go from something which is pretty much the T2 time down to 0. I see how far down I have to go for everything to work, how fast I have to make them. And for the gate and measurement fidelities, I take them from 90 upwards. And then for each set of parameters, we work out, does the code outperform the benchmark or not? And what we found is that, well, there's kind of two regimes. One is that if our gate fidelities are higher than 91% and our measurement fidelities are higher than 96%, everything works, yay! So that sounds really great, because look how low that is. But it's kind of a lie, because this happens when the timescale for our entangling gates is huge. So that means that our entangling gates here are going on for ages. And in order to keep the fidelity as high as 91% when you're running your gate for as long as the T2 time, is going to be difficult. So even though it looks nice and low, it's actually about as hard for an experimentalist to do as this 99. But that is at least a regime. We can have slow gates and low fidelities, although that doesn't mean it's easy. We could also have fast gates, the kind of clock speed you would expect more likely for a quantum computer, and that needs the 99s that we typically expect. So,
So you're saying that slow gates is better?
no, I'm saying that they're both, I mean, it's better for putting in an abstract and impressing people, but they're both really as bad as or as good as each other. And this one is better because it's actually more typical of what we'd need in a quantum computer. So this is really just, look, we get low fidelities, but we can't really trust them. And this is really what we'd need. So it's telling you that we need gate fidelities of about 99%, which is what we get if we take a Fowler paper with infinite code distance and do 1 minus threshold. So it's not really going to give anyone any huge surprises, but at least we found it in a different way, which is maybe a little more trustworthy. So for phase 3 experiments, it's just going to be the same thing, product state at the beginning, measurement at the end, but we're going to have to do a lot of syndrome measurements in between. So this is a very simple picture. It doesn't really show you there should be another step where you do all of the gates, and then you do these ancilla measurements. So now you're having to wait the amount of time it takes to do a measurement during every measurement step. So can we measure fast enough is a very big question, because measuring is typically slow, and we have this trade-off between how long we are prepared to measure and how good we want our fidelities to be. So do we want to do short and crappy ones, or do we want to do long and perfect ones? That's something that's going to have to be looked at a lot for phase 3, sorry. And also the syndrome will be too large for lookup table decoding anymore. So what kind of decoding algorithm will we use? So in the SFOR paper, there is an algorithm based on very simple rules, which can be extended to arbitrary times. If you apply that same algorithm to our case, where we only have a very short time scale, then their decoder basically does as good. So there are some regimes in which we do a lot better, but mostly their decoder is basically as good, which is really nice, given that their one is just like 3 lines of if this, do that. So it's likely that their algorithm could be very good there, but it does involve assumptions about what the noise model is, and we don't know how good they are. But that could also be a way to characterize noise in our system. A nice thing about this lookup table decoder is you get these 512 probabilities, which really characterize what the noise does to your system. They are the 512 most important parameters when it comes to noise. And you can look at those and wonder about try and extract some interesting data about what the noise is there. And one thing, so but that is where you get your answers from when you formulated your question, but you have to know what question to ask. And one question to ask could be, how well does the SFOR type decoder do in comparison to the lookup table decoding? Because the worse it does, then the worse our assumptions are. The assumptions that we made when we made that, well, I say we as a community, but the assumptions that Demeter and SFOR made when they invented that decoder. So
just to make sure I'm following, the actual number of parameters will be 1024, right? Because you'll have a class for each of the 4 possible logical.
Well, you only ever get access to half the syndrome, because so you've got 8, say, white plaquettes, which are the only ones that you get access to. So that's 238 is 256, if I'm correct. And then you get the 2 classes. Only 2, because only lying and not lying. So you've only got the 2 classes because you've only got one logical operator, because the other one is not accessible to you. So 512, but it's all order of 2, factor of 2. So
I was just thinking, I hadn't appreciated the other ones. I understand.
okay, so that is the end of that part, but now I'm going to plug something completely different, which is I made an app. Download it now. I made 2 actually. Download them both now. So as well as talking to experimentalists, I want to also talk to the public. So decoding is all about solving the puzzle that the syndrome poses. The syndrome gives you this puzzle, and you've got to work out, is the logical operator lying to me or not? So I've made a game based on QDIT surface codes. So this is one of the apps. You have to work out what number should be in these boxes based on the fact that they come in small groups that add up to a multiple of 10. So this is a very easy one. So anyone can do this. You don't have to have advanced degrees in quantum stuff to be able to try and solve this puzzle. So I've set it up that people can try and help us do quantum error correction. Because there's some codes specifically that are pretty heuristic, QDIT surface code, non-abelian anions, and so ideas contributed by the public could actually be useful in this. They could help you work out your rules in your Harrington type decoder. So currently, if you have a QDIT code according to this error model, who can achieve the best lifetime? If I do it with all of my knowledge and shit, and I cheat by knowing where the errors happened, I get this lifetime of 226. But some guy who didn't cheat got 861. So that just goes to show how useless we all are. In comparison with... Yeah, but he typically gets a lot higher than this. Like, if he got that, he would think, oh shit, I messed up. So he is pretty awesome. So yeah. He emailed me his name if you want to hire him as a grad student. Yeah.
But you did this also for the surface code, hire for QDIT?
Yeah, we can also do it for the qubit version, but so I do it for the QDIT version just because it makes a nicer puzzle, and we don't have minimum weight perfect matching for the QDIT, so there's more space to actually do good stuff. And also there's another one based on the non-abelian anions, which we're much worse at. So we've made this citizen science project. It's called Decodoku. So decode, and because it's a grid-based number game, Sudoku have inspired that. So check out our stuff. And we've just started a series of videos explaining the methods that we as scientists use on decoding. So Michael contributed to that yesterday. If you want to contribute a video, let me know. And also, I can't spell, and also if you want to try and reclaim the high score for us scientists from this Stefan Bordo guy, then go for it. Yep.
Another question. Is it just some optimization problem?
Yeah, just some optimization problem. Yeah, but but he's doing better than.
into the solver.
If you actually take any algorithm that we do and do it by hand, then you'll find out that they're really shit. So yeah, it's just some optimization problem, but we're doing very badly at them.
No, but
So
I just kind of, I would imagine that the guy just, formulated it and put out some software to solve it. No.
he's done a video of his thing. So if you want to see him get that 861, go to our YouTube channel, and you will see it happen live.
But I mean, it's gotta be hard to be, like, for the surface code to be like that.
Yeah. So that's why I haven't made it. Yeah. So that's why I didn't make it for that. I made it specifically for the non-abelian decoding, which we don't really know. We can't work out what the optimal threshold is. It's hard to even conceive of the question that could be answered there. But we can let people have a go. And it's not just about getting people to do our work for us, because we could probably think of the same things if we fought hard enough. It's also just getting people involved and knowing that this exists and whatnot. So, thank you for your attention.
So yeah, I got a high score of 22 so far. It's not actually very. Maybe I need to do the tutorial. I thought I could probably skip that.
Yeah. Well, I'd go for training games first, where you see the errors.
Right. So, are there any questions for James?
Mm-hmm.
So, in the example you gave, I think you were only detecting one kind of error. Is that right? Just Z errors.
Yeah.
And in a sense, that's what Martinez has already done.
Mm-hmm.
So, have you considered, how this would work when you're just taking both types?
Well, that would be when you did another layer of syndrome measurement, because that would give some sensible. Because we only measure one because we can only have access to one when we follow preparation by readout like this. Because.
Could you compare the y space and make a y space?
Oh yeah, maybe actually that's true. We can think about that, but then also the decoder becomes many factors of 2 higher, so we have to use a different decoder for that. So that would be future work anyway.
And I have a second quick one.
Yeah.
So you're mainly looking at error detection.
Yeah.
Correction. So have you worked at the distance 2 version? It might be more.
Well, yeah, the distance 2 is not too hard to imagine, but we haven't studied it specifically. Yeah, that's a good idea.
And I have a question about so you show the phase 2 right? You do 1 round of syndrome, phase 2 and phase 3, you do many rounds of syndrome, right? So I guess it's kind of coming back to Barbara's question. I mean, I would imagine something like phase 2.5 where you do maybe 1 round logical X and a couple more rounds, compare it to doing logical X on unprotected, right?
Yeah.
That would be much closer to fair comparison.
Yeah.
You have protection or not, because you kind of compare it to this time scale.
Yeah, the phases aren't really so discretized, and that the more you do, the better it is. But yeah, this is the very basic that I've been looking at. But more is better. Yeah.
So I'm interested to know more about this bias reduction technique you do on the surface code stabilizer where you kind of half change them so that they're way 2x and Z.
Yeah.
Would that also work for other codes? Would you also eliminate bias and white noise? And add some stabilizer to the way 0.3?
Yeah. So standing up on here in the spotlight, immediately I think yes, it would work. But it would have to be thought of in more detail.
Okay, if there are no more questions for James, let's thank him again. So,